Everybody, and welcome to another video of the Fourier Transform lesson handout. In this case, exercise number 8, we will do a peculiar exercise. In part A, we are given two systems with impulse response h1 of t cascaded out with another system, which is has a frequency an impulse response h1 minus t. This is what we are given, and they are asked us to select h1 of t in such a way that this system is equivalent to a single system with impulse response h, and it has to be a system which has a null phase. We will soon see what does this mean. Does it mean? And they are asking us to find which are the conditions that the response in frequency of h1 of t, which is capital H1, which are the conditions that the modulus of h1 has to meet, and the phase of the frequency response has to meet as a function of the frequency response that I want to obtain, which is capital H. Okay, so first of all, what does it mean, null phase? Okay, null phase means that the impulse response H, if we Fourier transform this, we will get the frequency response H, and as a complex that it is, it will have a modulus and a phase. Let's call the phase this. Well, so null phase means that the phase is null, so that the frequency response of the system H is just the modulus of H, or in other words, the phase is always zero, or in other words, the response is real. It has not phase. It's real, can be a real function of the frequency W. This is what null phase means. Another way to think on null phase is that if we input a signal to this system H, the output will be another signal that may change in terms of its modulus compared to the input, but the phase of the output signal will not change at all. It's a system that may change the modulus of the input signal, but will never change the phase of the output signal. Okay, but let's go and see what they are asking to us. Okay, they are telling that we want to make a system with response H of t, which is the cascading of h1 of t with h1 of t of minus t. And cascading, remember from the first part of the subject, means convolution. So we need to find again h1 such that behaves like this, with he being phase null. As we are talking on phases, what is wise here is to do the Fourier transform of this expression, and this will be in Fourier terms, it will be capital H of omega equal to capital H1 of omega, and the convolution in time, remember that it goes to a product in frequency. So this will be H1 of minus omega. Why do I put H1 of t minus t equal to H1 of omega? Because there is this symmetry property that we know the Fourier transform always has, regardless of how the h1 of minus t it is. Okay, now we are going to use an important property of all the systems that we have here, which is all the h So h1 and h2, all of them are real functions. They are real. And what this means, remember, is that real means that they verify the Hermitian property. Their frequency response are Hermitian. And our Hermitian means the following. Here we keep writing, this is h1 of omega. It means that h1 of minus omega, it's the same as h1 conjugated of omega. This is what Hermitian means. So because h1 is real, we can write this thing like that, Hermitian. And again, we can do that because h1, well, h2, there is no such a thing as h2, but h1 is real. If it were not real, we couldn't write this. However, this pass from h1 minus t equal to capital h1 minus omega, we can always do because it's a symmetry of the transform itself. You don't impose any restriction to h1. And we know that when we multiply a complex by its conjugated, the result is the modulus of that complex square. Okay, so we are done. Basically, the condition is here. The relationship between h1 and h is that one. We can write it the other way around, which could be the modulus of h1, which is the system that we need to find out, is the square root of the modulus, of the frequency response that we want to obtain. If h1 of t behaves in such a way that its modulus is the square root of the system that we have, then everything, the fact that both in series, in cascade like it is, will create a null phase system. So that's the only condition. Is there any condition for the phase of h1? Because they are telling me that I write this relationship and also any relationship with the phase. Well, there is nothing about the phase in all this development, which means that there is no condition for the phase of h1. The phase of h1 can be whatever phase, and just verifying the modulus this, we will meet the requirements of the system. So that's the only restriction that we have, or condition that we have to meet. Okay, let's go for part B. In part B, they are telling us that in this case they use three systems. They use h1 of t. In principle, h1 of t has nothing to do with the h1 of the first part of the exercise. It's another system. We have h2 of t, and over here we put again h1 of minus t. We put three systems in series, two of them being the same, but one with the axis in time change, and another system h2 in the middle. And they tell us that in this case, what we need to achieve, it's a single system, a single frequency or impulse response that they call h of t. And now this h of t has to be of type linear phase. So in this case, it's not phase null, but linear phase, that we will see what does it mean. And they give us another condition, which is h2 of this has to be of the type all pass. And again, they ask us which is the relationship between h2 and h1, and h2 regarding which is the relationship with respect to h1, and also with this the relationship of h1 as a function of h. Okay. Well, first of all, let's define what this all pass and linear phase mean. All pass and all pass system is a system that passes everything without any change at all. So if you write, for example, as a function of the frequency, you write the modulus of it, so the modulus of h2, all pass means that its frequency response is completely flat, and it doesn't change anything at all. This is what it means. What it means, all pass. Does it mean what happens with the phase? Well, with the phase cannot be anything, but all pass just refers that it passes the modulus without altering at all the modulus, without attenuation or amplification, and the phase it can change, certainly. And what does linear phase mean? Okay, linear phase means that the phase is linear. So remember that if the frequency response of h of t is h of omega, it will consist in a modulus and in a phase. And linear phase means that the phase, which is this function over here, is linear. It's a linear function. It's a linear function of the frequency omega. So phi sub h is a linear function of the frequency of omega, means that is of the type a constant that we can call it t0 times omega. This is what linear phase means. And typically a linear phase system is a linear phase that looks like its response in terms of the modulus. It's a response which is a linear straight line that goes through zero, and this angle has to be with the zero. The tangent of this angle we can call it theta. It's precisely the zero. This is what linear phase means. What happens to the modulus? Well, the modulus can be anything, but linear phase just is a condition for the phase. Okay, so explain that. Let's go and do the exercise. H of t, the overall system, which is the cascading of the three systems, will be the first system, h1 of t, convolve with the second system, which is h2 of t, and convolve with the last system, which is h1 of minus t. Again, we do the Fourier transform of this expression, and we'll get the frequency response of the system h of omega, which is what we want to find, is the frequency response of the first system times the frequency response of the second system times the frequency response of the third system. That we know for the symmetry property of the Fourier transform that this is h1 of minus omega. So far we haven't applied any condition at all from the conditions that we have. Again, in this system they tell us that all the impulse response are real, and this is what we are going to use now to convert this thing, because it's real. This is hermetic, which means that this is the conjugated of h1 of omega, so that multiplying h1 of omega with the conjugated of h1 of omega, then we will get a term which is modulus of h1 of omega square times h2 of omega. So far we have only applied the condition that the impulse response of h1 is real, to use the say that then the frequency response is hermetic. So far only that. Okay, so now let's use the two other conditions, that the system h2 is all pass and the system that we want to obtain is a linear phase system. Okay, so first condition, h of omega, a linear phase. So what does imply? We have said that h of omega, if it is linear phase, it will have a modulus h of omega, and then it will have a phase which is a linear function of omega. So it will be j omega t0, with t0 a constant. And the other condition is that h of t is an all-pass system, which means that its frequency response, h2 of omega, doesn't affect is a constant k in terms of the modulus. So it will be a constant times a phase that in this case we don't know what it is. Okay, these are the two conditions. Okay, so let's apply these two conditions to the relationship that we have obtained here. Okay, if we apply this over here, we will have on the left, we have h of omega. H of omega is the modulus of h of omega times a linear phase. And this is equal to a square modulus to the square of h1 of omega times h2, which is a constant times j linear and a linear phase, whatever phase, phi, let's call it phi sub 2, meaning that this is the phase of h2, phi 2 of omega. Okay, so if we equal the modulus of both complex functions in each side of the equality, and we equal the phases in both sides, we will get these two conditions. In terms of the modulus, we will get that the modulus of h1 of omega square, it's equal to the modulus of h1 of omega divided by k. K again is a constant for which the signal at the input of h2 is attenuated or amplified, depending on being k bigger than 1 or less than or lower than 1. And the second condition on the phase is that exponential of j omega t0 has to be the same as the exponential of j phi sub 2 of omega. These are the two conditions. Okay, so this one is already a final condition. This is part of the solution. And this one, we do a Fourier transform in time. We know that an exponential, it will be, So if we just take into account that h2 of omega, it's a constant times the exponential of j phi sub 2, this is what we got because it is a normal path, then applying this, h2 of omega will be the constant times aj omega t0. And now, if we make the Fourier transform of this, h2 of t is the Fourier transform of this, which is an immediate one, is k times delta of t plus t0. So these are the two conditions that they were asking to us. What is the relationship of h1 with modulus or with h of omega? And this is a condition in modulus, no restriction at all in terms of the phase. And the second condition that we are giving is we are giving the impulse response h2 as a function of, they were asking as a function of h1, but really you don't need, the condition is even more primitive, and it's just a constant of a delta change. Okay, so this is the second part of the answer. Okay, so I hope this exercise is clear. It's an interesting one, I think, because you practice these Hermitian and symmetry properties, and also we learn three very important properties: the null phase, the linear phase, and the all-pass concepts, which are very important concepts of systems. And these type of systems, the ones that are null phase or linear or all-pass systems, are very, very frequently used when working with signals and systems. Thank you for your attention, and I hope to see you in another video. Bye-bye.